Scientists are converging this week on the south of France to begin assembling what some call the world's largest puzzle.
Unlike nuclear fission used in today's power stations, fusion offers the possibility of clean nuclear energy.
We ventured into the heart of the world's biggest nuclear fusion reactor, a giant machine designed to unlock the sun's power here on Earth. It's a complex beast, humming with energy, where scientists are pushing the boundaries to create endless, clean power. What if something went wrong in this intricate ballet of technology? Could we be on the brink of a disaster? Join us as we explore the potential risks and rewards of this groundbreaking experiment and uncover what it takes to safely harness the power of the sun. Future energy frozen. The world's largest nuclear fusion reactor, ITER in France, has just been finished. However, it won't be ready to use for another 15 years. This $28 billion reactor has just added its final magnetic coil, but it won't be turned on until 2039. Scientists have announced that the biggest fusion reactor is now fully built, but it will stay inactive for the next 15 years. The ITER reactor has 19 giant coils, arranged into several magnets, and was supposed to start testing in 2020. Now, it looks like it will only start working in 2039. The delay means that fusion energy, led by ITER's design, won't be available soon enough to help with the urgent climate crisis. The postponement of ITER certainly isn't helping, said Pietro Barabaschi, ITER's Director General. Given the current environmental challenges, depending on nuclear fusion as a quick solution is not wise. But this isn't the worst part. This huge reactor is a team effort by 35 countries, including all members of the European Union, Russia, China, India, and the US. It holds the world's strongest magnet, which can create a magnetic field 280,000 times stronger than Earth's. The reactor's design is as impressive as its cost. It was initially supposed to cost about $5 billion and be ready by 2020, but it has faced many delays. Now, it costs over $22 billion. With another $5 billion needed for unexpected expenses. These issues have added to the 15-year delay. For over 70 years, scientists have tried to use nuclear fusion, the process that powers stars. In fusion, hydrogen atoms merge to form helium under very high pressures and temperatures, turning matter into light and heat. This produces a lot of energy without greenhouse gases or long-lasting radioactive waste. However, recreating star-like conditions in a reactor is extremely hard. The tokamak, the most common design for fusion reactors, works by heating plasma to very high temperatures and keeping it in a donut-shaped chamber using strong magnetic fields. The challenge is to keep the heated and unstable plasma stable long enough for fusion to happen. Natan Yavlinsky, a Soviet scientist, made the first tokamak in 1958. Since then, no reactor has been able to produce more energy than it uses. Managing plasma hot enough for fusion is a major hurdle. Fusion reactors need to reach temperatures much hotter than the sun, yet at much lower pressures than those at the core of stars. For example, the sun's core reaches about 27 million degrees Fahrenheit, 15 million Celsius, with pressures about 340 billion times greater than Earth's sea level air pressure. Heating plasma to these levels is relatively easy, but keeping it contained without damaging the reactor or stopping the fusion process is a technical challenge. This is usually done with either lasers or magnetic fields. Here, the biggest nuclear fusion reactor in the world is being built. I'm currently standing inside the assembly hall of the International Thermonuclear Experimental Reactor, ITER, located in southern France. Just behind me, teams of scientists and engineers are hard at work trying to recreate the processes that occur inside the sun. It's an awe-inspiring sight, with cutting-edge technology and brilliant minds all focused on a single ambitious goal. This isn't just a regular energy project. It's a massive $22 billion scientific venture. Many countries are working together to change how we generate power on Earth. The goal of ITER is to create a new, sustainable energy source, which is crucial because global energy use is expected to nearly double by 2050. We need to cut down on our use of fossil fuels, which are not only running out, but are also harmful to our environment. But this isn't the most ambitious part. Some experts believe that controlled nuclear fusion might be the ultimate answer for energy. However, there's a big challenge. So far, no fusion reactor has produced more energy than it consumes. ITER aims to solve this problem, and, if successful, it could dramatically change our world. Imagine a future where our energy needs are met by a source that's clean and almost limitless. However, the path to achieving this is fraught with difficulties. Nuclear fusion, the same power that fuels hydrogen bombs and the sun, might be the solution we've been searching for, offering abundant, clean, and endless energy. In November 1985, Mikhail Gorbachev from the Soviet Union suggested to US President Ronald Reagan that they should form an international group to harness fusion energy for peaceful use. By the next year, the European Union, Japan, the Soviet Union, and the United States had agreed to design what is now known as ITER. This was a monumental decision, setting the stage for a global collaboration that continues to this day. This international effort now involves thousands of engineers and scientists from 35 countries. They are working on a massive 23,000-ton reactor, aiming to create a small sun here on Earth to power our planet. If you think this sounds big, you're right. The scale of the project is staggering, with components being manufactured and transported from all over the world. The logistical challenges alone are enormous, but the potential rewards make it all worthwhile. However, the scale isn't the only hurdle. Unlike regular nuclear reactors that work on fission, splitting atoms to release heat and radiation, a process that fuels both destructive atomic bombs and current nuclear power plants, fusion works differently. Fusion combines atoms using plentiful elements like hydrogen isotopes from water. This process occurs at extremely high temperatures, similar to the conditions found in the core of stars. Achieving and maintaining these temperatures on Earth is a significant technical challenge. But this isn't the most challenging part. The immense heat from fusion reactors could be used to generate steam, which in turn drives turbines and generators to produce electricity. If successful, this technology could provide a limitless supply of eco-friendly energy that doesn't depend on sunny or windy conditions. This means a stable and reliable source of power, regardless of weather or time of day. Imagine the impact on our cities, industries, and even everyday life, where energy is both sustainable and abundant. Challenges of fusion power. However, the path to harness fusion energy is filled with scientific and engineering obstacles. The materials used in the reactor must withstand extreme conditions without degrading. The plasma, a superhot gas where fusion occurs, must be contained and controlled within powerful magnetic fields. Even small instabilities can cause the process to fail, making precision and control crucial. Despite these challenges, the potential benefits of nuclear fusion are too significant to ignore. Fusion offers a way to produce large amounts of energy without the harmful byproducts of fossil fuels or the long-lived radioactive waste of fission reactors. It could significantly reduce our carbon footprint and help combat climate change. The success of ITER could pave the way for future fusion power plants, changing how we think about and use energy. The construction of the world's largest nuclear fusion reactor is not just a remarkable scientific endeavor, but a critical step towards a sustainable energy future. The collaboration of nations, the cutting-edge technology, and the sheer scale of the project all highlight the importance of this mission. If ITER succeeds, it will mark a turning point in our quest for clean, abundant energy, reshaping our world for generations to come. But until then, the journey is filled with challenges and uncertainties, making it one of the most exciting and vital scientific projects of our time. Creating a big and effective nuclear fusion reactor on Earth is a really tough job. It needs a machine that can handle temperatures 10 times hotter than the sun's core and forces twice what's needed to launch a space shuttle. This means the reactor must be super strong, using tons of concrete and advanced engineering. When the reactor is turned on, hydrogen atoms are shot into a vacuum chamber. Then, a huge superconducting magnet around the chamber is switched on. This separates the electrons from their atoms, creating plasma, a state of matter similar to gas. This plasma is heated to an incredible 150 million degrees Celsius. At these high temperatures, the atoms fuse together, releasing a huge amount of heat. But this isn't the most impressive part. The energy produced by nuclear fusion is 4 times more than nuclear fission, and 4 million times more than burning the same amount of fossil fuels. The ITER tokamak, planned to be the biggest and most powerful fusion device in the world, will have 1 million components and 10 million parts. The member countries of the ITER project make and put together all these parts, which are then brought to a massive 445-acre site in France. Putting these parts together is like building a very complicated Lego set, but much bigger. The scale of this project is mind-boggling, and it requires a high level of precision and coordination. I'm Colette Ricketts, the Deputy Head of the Project Control Office for the ITER organization. My job is to make sure all the parts arrive on time in the right color, shape, and size. I organize what is basically a gigantic, complex Lego set. Each piece is crucial, and even the smallest error can cause significant delays. We had to adapt 104 kilometers of roads, now known as the ITER itinerary, to transport these huge parts. We built bridges, widened roads, and even changed roadside structures. We also arranged police escorts to manage the transport of these large parts. The logistics behind this are incredibly complex, involving careful planning and real-time problem solving. But that's not the hardest part. Once these parts get to the site, they are assembled in a huge hall. Giant cranes lift and move the parts into the reactor. Even though the basic idea of the facility has stayed the same, the details often change due to global factors like pandemics, Brexit, and political shifts. This means we constantly have to reschedule and adjust our plans. It's a dynamic environment where flexibility is key. Every week brings new challenges. We deal with unforeseen delays, supply chain issues, and changes in regulations. But we always find a way to adapt and keep moving forward. Managing this project requires a balance of strict organization and the ability to think on your feet. It's a constant juggling act. Most of my work involves changing our strategies to fit the ever-changing conditions, a tough job that never goes as originally planned. Managing this project is the ultimate task for someone who loves construction as much as I do. It's not just about building a reactor, it's about overcoming obstacles and achieving something extraordinary. This is a project that demands dedication, creativity, and a relentless drive to succeed. But let's not forget the ultimate goal. Creating a working nuclear fusion reactor has the potential to revolutionize our energy supply. It promises a nearly limitless source of clean energy, which could have a profound impact on our planet. This isn't just a construction project. It's a step towards a sustainable future. Every person involved in this project understands the importance of what we're doing. The stakes are high, but so are the rewards. We're not just building a machine, we're making history. And that's what keeps us motivated, despite the challenges we face. Imagine trying to get one country to agree on a big project. Now imagine trying to do that with 35 different countries, each with its own language, culture, and way of doing things. It's a huge task that requires immense coordination and understanding. But here's where Think Project steps in to help. These countries have come together because they all know we need to tackle environmental problems. They see fusion energy as a way to get steady and reliable power, which could be a game changer for the planet. This shared vision brings them together, despite their differences. So, they are joining forces in an amazing cooperative effort. At the ITER project's headquarters, people speak about 45 different native languages. This makes things complex but also very interesting. Each day, teams from different parts of the world communicate and collaborate, blending their unique perspectives and expertise. It's like a giant puzzle where every piece is crucial. Challenges of fusion power. Behind the scenes, there are countless people involved in all the concrete, magnets, and metal. They are building, shipping, and putting together millions of special parts. Imagine the logistics involved in coordinating the delivery and assembly of these components from all over the world. It's a massive undertaking that requires precision and dedication. However, there's an even bigger challenge. All these different contributors need formal agreements to ensure they get paid and their work is recorded correctly. Think Project manages these agreements for almost 400 users from 30 organizations and those 35 countries. This part might not be the most exciting, but it's the glue that holds everything together. Without these agreements, the project would quickly fall into chaos. But here's the big challenge. The stakes are incredibly high for ITER, with organization being crucial. A lot of money has been invested in this project, marking a pivotal step from fossil fuels to renewable energy. If successful, ITER could pave the way for a cleaner, more sustainable future. This makes every detail, every agreement, and every piece of the puzzle vitally important. The pressure is on. This gigantic project is set to start up in 2025, aiming to generate plasma. The big goal is to achieve net energy, which means making more energy than it uses, even if only for a few seconds. Achieving this would be a monumental step forward in energy science, proving that fusion power is not just a dream, but a feasible reality. And this is where things get really interesting. If ITER succeeds, it could change the world's energy landscape forever. It's a beacon of hope in the fight against climate change, showing that international collaboration can lead to groundbreaking advancements. This project is more than just a scientific endeavor. It's a symbol of what we can achieve when we work together towards a common goal. After finishing this small task, the next big challenge will be to use the energy from fusion in our current electrical systems. It's like figuring out how to plug a new, powerful engine into an old car. But this is something we won't see for a few more decades, and future reactors will probably handle it. This step will take a lot of time, research, and new technology to make it work smoothly with the systems we already have. ITER isn't the only group trying to make nuclear fusion work. Many groups and private companies are racing to find a way to make fusion energy a reality and compete with fossil fuels. The recent U.S. infrastructure bill even includes several sections for nuclear energy research and development. These efforts show how serious and widespread the interest in fusion energy has become. Companies and researchers are pushing hard to be the first to crack this tough nut. But here's the tricky part. Even if they solve it, we still need to figure out how to make it affordable and practical. When someone figures out the right approach, we could produce a lot of energy without carbon, which would greatly reduce our dependence on fossil fuels. This clean energy could help fight climate change and provide a stable energy source for the future. But it will take time, and lowering the costs of renewable energy might speed things up. Imagine being able to power cities and countries without harming the planet. That's the dream, but getting there is a marathon, not a sprint. Reducing renewable energy costs now could pave the way for faster adoption of fusion when it becomes available. Thinking about a future where our kids and grandkids have a good life depends on fusion energy. It's the key to moving forward. Standing here in this reactor, a place that could change our global energy scene, really shows how important the construction industry is. Every beam, every bolt, and every piece of this reactor is a testament to the hard work and dedication of construction workers. This progress relies on the hard work many of you put in every day. Your contributions are not just building structures, they're laying the foundation for the future of energy. Years from now, this place might be seen as the starting point for a new kind of energy on Earth. Honestly, it's incredibly exciting. But this is just the beginning of a long journey, and there's still much to be done. Imagine telling your grandkids you were part of the team that built the first fusion reactor. The story of this reactor could become a legendary tale of innovation and perseverance. But let's not get ahead of ourselves. The path ahead is full of challenges and unknowns. Each step forward brings new hurdles to overcome, from technical issues to financial obstacles. Yet each small victory, each problem solved, brings us one step closer to that clean energy future we all hope for. So while we stand at the brink of something amazing, it's important to remember that this is a collective effort. Every bit of progress is a shared achievement, and every setback is a shared challenge. Is the pursuit of nuclear fusion a viable solution, or merely a scientific fantasy? Share your thoughts in the comments below. Don't forget to like and subscribe for more.